Hello, my dear students. Today we will learn a theorem from the chapter Circle. So, look here, the theorem number 1. A tangent to a circle is perpendicular to the radius through the point of contact. So, if you look the figure, I have taken a circle here. We can say the center of the circle is O, and I need to draw a tangent. So, let us take here a point below here. Take a point here, suppose P, and through the point P, we draw a line like this, AB, and this line AB is called tangent to the circle at the point P. Okay, so you have to know the definition of the tangent. What is a tangent? A tangent is a line which intersects the circle only at one point. A tangent is a line, a tangent is a straight line that intersects a circle only at one point. If you look here, this straight line AB intersect the circle only at the point P. So AB is a tangent to the circle at the point P, and this point P is called point of contact. And now from O we join up to the point P, then this is called what? Radius. This is what? Radius. As you know, the straight line joining the center to a point on the circumference of the circle is called its radius. So now we have in the figure, see, this OP is the radius and this AB is the tangent at the point P. So if we read here, so a tangent to a circle, this AB is the tangent to the circle, is perpendicular to the radius. See, OP is the radius. That means we have to prove that tangent AB is perpendicular to the radius OP at the point of contact P. Point of contact means the tangent intersects the circle at a point. That point is called point of contact. So we write, see what we have taken here. We take, see, given, so that means we get from this statement, we have to take given a circle, say we name the circle C with center O and radius R. We read it like this. A circle C, name of the circle is C with center O and radius R, and a tangent. What is the tangent? AB. AB at the point, tangent AB at the point P. Then what we have to prove? We have to prove that this radius and this tangent is perpendicular. So we can write OP is perpendicular to AB. To prove OP is the radius, perpendicular to the tangent is what? AB. This is the symbol of perpendicular. Okay, we read it, OP is perpendicular to AB. OP is the radius, it is perpendicular to the tangent. So if we see the theorem again, a tangent to a circle, this is the tangent, is perpendicular to the radius. This is radius at the point of contact P. Now this picture is not sufficient to prove this, so we need to draw some extra part. We call it construction. So what will be construction? See, on the line AB, suppose we take a point here Q other than this P, okay, and we join this O and Q by a straight line, see, like this, and then this line OQ cuts the circle at this point. We name it what? Say R. So what we have drawn, we write here the construction. What is, we take any point Q on AB which intersects the circle at where I. And now the proof, see how we start the proof. Look here, this OP is a radius of the circle, and here this OR also is the radius of the circle. Now we know in a circle there are so many radius and all the radius are equal. So when we write the proof, we start from here. This OP is equal to OR. Proof. We can write here, since OP is equal to OR. Why are they equal? We can write here radii, R-A-D-I-I. Radii means plural of radius. So radii of the same circle. So these two radius will be equal. And now I write this, OQ is equal to what? OQ is equal to what? We can write here OR plus RQ. OR plus what is RQ. Okay, if you look the figure, OQ is equal to, with OR we add this RQ. That means this OQ is bigger than OR. So we can write here, therefore OQ is bigger than OR. Therefore we can write OQ is bigger than what is OP, because OP is equal to OR. So when OQ is greater than OR, that means OQ is also greater than OP. So, and oppositely we can say, when OQ is greater than OP, we can say OP is smaller than OQ. Okay, this OP is what? Smaller than OQ. Now see, this Q, instead of here, we can take it here, we can take it here, we can take it here, and in that case we can get so many straight lines. Okay, but out of all those straight lines, we will see this OP is the shortest of all such straight lines drawn from the point O to the line AB. So we can write here, so hence this OP is what? Is the shortest of, this point you have to mention, is the shortest of all such straight lines, that can be drawn from O to any point on AB. So see, from O up to AB we can draw so many straight lines like OQ. If Q is here, we can get another. If Q is here, we can get another. But out of all the line, the shortest line is what? OP. So we are writing here, hence OP is the shortest of all such straight lines that can be drawn from the point O to any point on AB. Now, we know this point, we have to use the theorem that you have done earlier. So we can write like this. We know of all the line segments, drawn from a point to a straight line from this point to this straight line at any point. So we can write here, of all the line segments drawn from a point to a line outside the point, outside the point, the perpendicular is the shortest. This sentence you have to remember. The perpendicular is the shortest. So see, from O on AB, suppose we can take so many point, and if we join them by line, then we can show that out of all the lines, this OP is the shortest. And if OP is the shortest, from here what we know? From all the line, the shortest line is the perpendicular. That means we can say here this OP is the perpendicular to AB. So here we will write, therefore OP is perpendicular to AB. So we can write here approved, and we can conclude that the tangent at any point is perpendicular to the radius at the point of contact. Okay, so that is the proof of the theorem. Okay, thank you, my dear students.